The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you. As Kim said, I'm relatively experienced. I've done TiltUp for about 18 years, mostly in the big box world. And so I volunteered, got nominated to give a little presentation on TiltUp hacks. And I wanted to approach it as kind of a, here's what I do, and this is the methodology that I use, because there are differences. And I know, and specifically in terms of analysis, Jeff is going to go into some of the nuances of how you design tilt-up panels. So this isn't a real technical presentation. This is more kind of big picture, but I'm also kind of assuming that you've got some experience in the tilt-up world, and especially in big boxes. But if there's something that I say that doesn't make sense, you know, feel free to run up to the mic and ask questions. So here's a real overview of what we're going to talk about. We'll try and get everybody on the same page with going over some of the starting points. I'll go through a few of the things that we look at in terms of loading, important stuff, not important stuff. Run through a little bit of analysis and show you some of the options and methodologies of what I think is the right way to analyze panels. And then finally, time permitting, I'll show you just a few of the details that I've accumulated over the years for regular conditions and a few oddball conditions. So, big box tilt-up, what are we talking about? We're talking about buildings like this, that, all that, big boxes. Some bigger than others. We're not talking about that, or that, right? Those are all tilt-up buildings, but not big boxes. They're different. We're also going to talk a little bit about the structural engineering of the building, because that plays a large part in designing the tilt-up panels, and just a few things that I've learned along the way. So, some rules, set the table. First rule of structural engineering is thou shalt have a load path, or a load path will be provided to you. Right? The load's going to go where it's going to go. You try and control it, you try and account for it, but it's going to go where it's going to go. Second thing, on tilt-ups, most importantly, is the panel is cracked. I can't say that more importantly. The panel is cracked. Panel is picked up after 4 to 7 days of curing on the ground. It's very green. No matter how much cement they add to it, it's not up to design strength. So the panel comes to you cracked. So just know that. And the last one is, no matter what rules and regulations, because there's a number of different ways to analyze a tilt panel, concrete doesn't care. The concrete doesn't care that it's a slender wall. The concrete doesn't care that you called it a column. It is what it is, and it's going to behave that way. So let's talk about what loading we're going to cover. We've got the usual loading, the stuff that's covered in ASCE with whole chapters like snow, wind, and then you've got the unusual loading conditions like panel-on-panel bearing, nested panels, thermal effects, snowdrift. A little bit of my soapbox here, but if you're designing a big box, design it without parapets. Parapets are evil. Anybody who's done this knows what I'm talking about. A small parapet, 2, 3, 4 feet, can have dramatic effects on the snow loading, wind loading. It's not necessary. You're not screening the RTUs from something. So whatever you can do to control that, just understand, get rid of parapets, your life will be better. The second thing on snow loading is, even when your snow isn't controlling the design, you got to look out for snowdrift. So for instance, I'm going back, kind of jumping back and forth here a little bit, but so when you have, let's say you're in Virginia or Tennessee where ground snow load is 10 PSF, you can still have significant drifts because your upwind length can be 2,000 feet, 3,000 feet. So you can get an 8-foot tall drift even though snow load didn't control 90% of your design. You could still have gigantic snow drifts up against your panels. But if you get rid of the parapets, then that goes away. Another thing to cover real quick on snow, and ran into this on a couple of projects. Keep an eye out for RTUs. There's a limit in ASCE 7 that says anything less than 15 feet doesn't need to be designed for snowdrifts, which means if you have an RTU that's 15 feet long or a screen around an RTU that's 15 feet long, guess what you got? You got snowdrifts. And the last one that trips people up is canopies. A lot of times you'll see them on a long loading dock wall. You'll see a little canopy over there to cover the backs of the trucks. That canopy is about mid-height of the panel. That canopy snowdrift can be 8, 9, 10 feet tall because it's not capped. You've got 15 feet of panel above it. So be careful because that loading can be several kips without even trying too hard. Wind load, I've designed a few buildings in high wind regions, so I'm not an expert in wind, but I've dabbled. First thing I will say is, in looking at panel design, individual panels, individual components within a panel, I always treat a panel for components and cladding wind. You can have a panel that's 1,500 square feet, but when you're designing the elements within the panel, when you've got a jam on the left side of the panel, it's affected by the loading on that side. It doesn't get affected by the main wind force where you can average it over a larger area. So no matter what Factory Mutual says, a panel is component. Now this can make about a 30% difference in your wind loads, so I'm saying that this is what I would do. Coming back to parapets, still evil. But if you've ever done a design example with the, I guess ever since the 05 or the 02 ASCE 7, they gave us a multiplier for a parapet effect where you get the Bernoulli effect, where you get a pressure, positive and negative, and a 1.5 multiplier on your wind. You can take a building that's 30 feet tall at the panel edge, drop your entire roof 3 feet, right? You didn't change its profile other than making the relationship between the building and the parapet a little taller so you actually have a parapet. You can increase your base wind load by 30 to 50%, right? You didn't change the profile of the building, all you've done is move the roof down, but according to ASCE 7, you've got that increase can really kick your butt. The other thing on wind loads that comes up, more specifically in connections, but don't forget, in a wind load scenario, you're gonna have loading at 3 directions at one time. Right? You're trying to develop or check the in-plane connection to develop your in-plane diaphragm shear into your in-plane shear wall. Don't forget you also have uplift and side wind pressure at the same time. So if you got one component that's doing all 3 things, make sure you've accounted for them all. Okay? The last thing is one thing that I know rookie engineers make a mistake a lot is trying to figure out in components and cladding charts what my influence area is. So you're designing a 1-foot strip and it's a 30-foot tall panel. You say, oh, I've got a 30-foot tall influence area. That's not correct. What ASCE 7 says is the minimum area you have to account for is the height times the height over 3, right? So that same 30-foot tall or 30-foot square area is actually 300 square feet. So that'll reduce your wind loads by 20 to 30%. Seismic, I'm sorry to say to all those in California, the rest of the country does have seismic too. We experience it, and in big boxes, you can have a relatively low acceleration and still be controlled just because your mass compared to the wind load exposure is so much. You're talking a 500 by 500 foot building with a 10 PSF mass. It doesn't take much acceleration for that much mass to get activated. So, in designing for a seismic event, the first thing I try to do in trying to figure out the start of my building is figure out what my panel thickness is going to be. Panels are going to be about 30 to 50% of my overall roof mass. So accounting for that out of plane load, I've got to be careful what I'm doing. Now it's a fight, right? When you want to do the connection design, when you're trying to do the embed, you like to have a nice thick hunk of concrete to grab a hold of. But every inch you add to that panel's just going to increase your base shear and give you more to deal with. Especially in seismic, you'll find your in-plane overturning can really be a pain in the butt. Second quick topic is your out-of-plane connections. Don't forget to carry the two different seismic loads. So when you're designing your panel, you've got your main seismic, which is FP, is 40% of your 40% SDS times the weight of the panel. Right, you've got that out of plane. But if you have a flexible diaphragm, and I don't know too many big boxes that don't, you have a completely different A sub P, R sub P factor. And then if you're unlucky enough to have post-installed connections, you have another set of factors that's even higher. So be careful with keeping track of all your loads. The real mass of the panel has to do with, the other topic is in seismic. So you've got your mass of your walls, you've got your mass of your roof, and you're dealing with that analysis. If you look at the FEMA document that recently came out with flexible diaphragms, strong walls, it deals a little bit with an analysis for that, but the way I've always treated it is if you look at it as a single degree of freedom system, okay, your diaphragm is going to be humongously flexible, right? And so the period of your building and the mass that's associated with that is going to be almost completely in that diaphragm. So when looking at what the stiffness of my building is, I try to look at what the actual displacement of my diaphragm is and not just take a look at, if you were, say, doing a 3-story building, you might look at the drift of my brace to get an initial seismic drift. Looking at a big box, you want to look at what my maximum displacement is going to be at my roof, because that's what's your real period. And then the last thing in seismic, and this comes up a lot, is when you're dealing with the short wall of a building, right, you're going to have in-plane loads that can be 2.5 to 3 kips a linear foot. You're going to have panel overturning. The question is, how do you deal with it? Probably the most cost-effective way of dealing with it is stitching panels together. So you got 2 or 3 panels, so you got 90 feet of shear wall acting uniformly to overturn, versus trying to anchor each individual panel for the 15 or 20 kips, and then trying to figure out at the foundation, well, if I've got 20 kips up and I got 20 kips down, the heck do I design that grade beam for, and how do I get that force across the joint? So most engineers, they try to stitch panels together, but be warned, those stitching connections they can crack, they can interfere with your vertical reinforcement. There's a lot of nuance and fun that gets involved with that. Dead loading, as I talked about a little bit in the seismic loading, sometimes dead loading is your friend, sometimes it's your enemy. So when designing big boxes, I always carry kind of 3 different loads. I've got the design load for the girders, I've got a design load for the joists, and then when I'm backing into what's my uplift to design my footings, I have the real load. So usually I account for 3 to 4 to 5 pounds per square foot of fire sprinkler, so that way when the fire protection guy gets in and actually does the design 2 months after your steel's already been reviewed in shop drawings, you don't have to go back and figure out how to retrofit for every 2-inch and 3-inch line. But you got to understand that while you've upsized the joists and girders for that load, it's not actually there. So when you're checking your footing, make sure that you've accounted for what you expect to be there. You can also do the same thing in seismic. I usually don't in my initial design. But again, if you're carrying 5 PSF for collateral for fire protection, which all the wet pipes in the building are added up was 1.5 pounds, you could reduce your base shear. But I usually save that one for later on, and if I have trouble making something work. So seismic, again, when you're dealing with dead loads, you want to account for it conservatively, but it's going to be sometimes working against you. The other thing to remember, and especially I'm looking at people who've done buildings that have process designs where someone says, oh, there's a 30 PSF collateral to account for conveyor loading. Understand that 30 PSF is actually going to be hung from every 3rd joist. So that 2-kip load has to be dealt with as a 2-kip load, because the joist girders, whatever, are going to have to deal with that individual loading, and it's a different animal, and doing it after the fact is a giant pain in the butt, which is something I was dealing with just before I came here. Some unusual loading, some stuff that definitely didn't get covered in my coursework, and you run into it a little bit in the TiltUp world. So, thermal. Big boxes, especially these 1,000,000 square footers, they're going to have expansion joints. First thing I'll say is there are a couple of different ways of calculating and figuring out how to size your expansion joint. But as far as the tilt-up concrete is concerned, it doesn't matter. It's nice if you have a panel joint where the expansion joint is, but it's not necessary. The reason I know this is take a 30-foot long wall, 30 feet tall, and try and push it over 1.5 inches. How much force does it take, right? It's going to take 200, 300, 400 kips to deflect that panel 3 inches. So no matter what your thermal load actually is, trying to carry that expansion joint through the wall's just not going to move. It doesn't matter what your thermal load is. So I don't carry my expansion joints through the wall. Plus, it's a hell of a thing to try and caulk a 2-inch joint. Contractors love that. The other thing is, if you have a building that is, say, deeper or larger than what your calculations say, you need an expansion joint, but you can't get one for whatever reason. If you have to constrain your building for thermal expansion and contraction and not let it expand, you have to deal with that force. But I'll tell you, you're chasing your tail. It's kind of dangerous because the amount of force developed, right, is proportional to the area of steel, PL over AE, right? For elongation, the only way to resist it is to add more A, which adds more force. So hopefully you don't chase your tail all the way to the ground. Diaphragms, pretty straightforward stuff, but in dealing with your panel design, if you're assuming a fixed base, and I will tell you don't, but if you're assuming a fixed base, you have to deal with what that diaphragm is going to do to your panel, both in terms of what the diaphragm is going to push on your panel. So you have forces that are coming from the diaphragm, not the other way around, which is usually how we deal with out-of-plane forces. But the other thing is thinking about your load path, especially in a seismic world where you maybe have, on the West Coast, you're going to have a hybrid wood roof. Thinking about your sub-diaphragm action and all your connections. Just make sure that you've got your entire load path in your panel design, out of your panels, embeds, into your joists, joists into the diaphragm, diaphragms into the sub-diaphragms. So make sure you've got a load path, right? That's the first law of structural engineering. Soil loads, I'll tell you what my typical behavior is, and that is, you know, the typical 4-foot tall loading dock panel, right? Your bottom of footing is 5 feet below finished floor, or your top of footing is. You can treat that as fixed, okay? But in doing that slab connection, you've got to account for the fact that you've got all that soil load there adding to it. So if you have a, say, high wind region or high seismic region where you're really counting on that slab connection to take the out-of-plane load, don't just stop your analysis at finished floor. Make sure you account for that reaction. Make sure you account for it as an at-rest pressure. I had a job recently I looked at that had a problem where they hadn't correctly dialed it in, and the soil deflected the panel about 1/2 inch to 5/8 of an inch at the base and about 2 inches in the mid-height. And that was just from the soil over time pushing and pushing and pushing out the wall. It broke the dowels off, which was the issue. The other thing is, if you do decide to try to span those footings or those panels from the footing to the roof, make sure you've accounted for it. Yeah, it's in the bottom 5 feet of your panel, but if you're not tying back to the slab and trying to make it span, which isn't my recommendation, but if you're doing it, make sure you've accounted for it in the same way that you would for all the other loads, okay? It's a 1.6 factor in LRFD design. It can really impact your deflection. The last one in the unusual loadings is, we see this in big boxes where you have the office element and they want to have a nice big glass wall somewhere, but they want tilt up above, they want 12, 15 feet of glass, and they want a nice 100-foot ribbon of glass so they can have a beautiful little office right next to the 1 million square foot building. When designing those panels, always bare, okay? Bare concrete on concrete if you can. Set back a panel edge so that your flying panels that come over the top, they sit on other tilt-up panels. It's more stable during erection, it's easier to brace, you spend less time with a crane up in the air and a guy out there in a welder trying to fix things together. And the absolute worst is trying to drill in epoxy some bolts. So whenever you can, bare it. And if you can't bear it on the tilt-up panel, put a seat on it. I like to use like a W12, but when you've got a panel sitting on another panel, you want a bearing type connection, even if it's bearing on steel that transfers into the panel. Last one, cantilevering panels, okay? So screen walls, retaining walls, you can do it. When you have a cantilever panel, there's a detail I'll show you later, but the idea is basically you build it in the tilt-up world with the panel first, then you pour the footing around it. You want to account for all the behaviors of the panel. Slender wall analysis doesn't really work. Your conventional concrete analysis here. And the last thing on cantilevers is on that canopy we talked about in snowdrift. That canopy isn't going to, if you had to retrofit a canopy in, it's not generally going to upsize your steel too much, but it is going to have an impact. It can really have an impact on the cranking a point moment in the middle of your analysis, but the real issue is what it does to your deflection. Oh, last one. Nested panels. This is, you see a lot of this now where architects want to break up a 2,000-foot wall by pushing some panels in and out, whether they're push back the thickness of the panel so you have like an overlap, or if you have a partial height panel that is attached to the outside. What we typically would do would be, if you need a 16-inch wall element, would be to pour an 8-inch panel and then pour the structural panel behind it. Pick up the structural panel, put the other panel on the outside, and connect through. So it's just basically a piece of thick veneer, okay? The idea here being, again, everything is a bearing type connection, and if you're not attaching to the roof, make sure you got your panel-to-panel connections working in the right direction. Some quick tips on analysis. Slender wall analysis. This is the preferred, and I'll say correct method of designing tilt-up, but it's not the only way, okay? In the wall section, you can look at a panel as a slender element, as a not slender element, but still a wall, or as a column element. Those are all available to you. It's a piece of concrete. The concrete doesn't know that it's tilt-up. In terms of the not slender analysis, probably the biggest thing is following the rules. So a lot of times you get kicked into not slender analysis when your axial load is greater than the 6% limit, right, for tilt-up. When you're between 6% and 10%, you have to design it basically using finite element or the moment magnification method. Just make sure that you've accounted for it, for all the moment magnification. So it's kind of the same analysis as slender wall, where you do some additional moments created by the deflection of the panel. I will tell you though that the rules are a little gray when you're between 6% and 10%, whether you're a column or a wall, in terms of how it's tied, how it's supposed to behave, and what the prescriptive requirements are. And then when you do get into columns, probably the biggest thing in columns to look out for when you have an axial load greater than 10% is in slender wall design, you can spread that load out, right? You can take it, and as long as you don't have a jam or anything, you can keep widening and widening the load until you get enough panel to get to 6%. But sometimes you're restricted by jams. When you're stuck designing something as a column, even if you have concrete for 100 feet in both directions, ACI says you can only treat the column as the area of the cage plus 1.5 inches on both sides, which means you may get stuck with, if you're greater than 6%, you may get stuck with something that's only 18 or 24 inches wide, where slender wall would have been okay. Point loads, kind of the same thing. The one thing here is on the moment magnification method, there's a term called P sub C, that's the Euler buckling limit. When you approach the Euler buckling limit, it is essentially the axial max for the panel, and it can really, really limit your design. So whenever you can, jump back into slender wall. A few details to run through real quick at the end of my presentation. Some gravity details. I love pockets. Pockets are great. Pockets are easy to construct. The only thing on pockets I would say is I always put the load at the face of the panel, because that's where I think the load's going to get into the panel. You'll notice on this one I have struts. We like to use struts for the deck bearing side. I think it's a more constructible detail. Gives you a little bit of redundancy too as a structural engineer. I like redundancy. For your hybrid wood roofs, account for your out-of-plane loads, your sub-diaphragm action. Make sure you also have a good load path for your in-plane loads. They love to put channels on the wall. Bearing type connections. Again, there's my W12 seat. I hate stiffened angles, so a W12 does the same work. Base connections. You've got your typical loading dock. You've got a veneer panel showing the Connect EZ. And you've got kind of your typical cast-in detail. I like the cast-in details where I can connect it. It's nice and redundant. High seismic loads, whether you've got an overturning issue here, where you're trying to develop a high point load reaction on the end of a panel, or you're trying to drag something into the panel. Using rebar to help develop into the horizontal reinforcement of the panel is a good way to get the forces across. The other one is the panel-to-panel stitch. I stole that one from the precasters, but wherever you can use a rod, it's going to cut down on the cracking. I know you guys don't like it, but I tell you, the thinner the piece of steel is, the less heat shrinkage you're going to get and the less cracking you're going to get. But they suck. They really do. There's just too much rebar there to deal with. Cantilever connection, use temporary footings, space periodically, and then cast the bottom of the panel in. Hey, the panel doesn't care. It's a retaining wall. It's going to do what it's going to do. And then when you have one of those bearing type connections, don't forget to put some details in there to hold the panels to each other to make sure you've got an out of plane load path. And then when in the corners, I like, especially on big boxes, I like to tie my corners together, because over time the panels are going to deflect a little bit, and that caulk joint at the corners can open up a lot. So I like to touch them together, keeps that caulk joint nice and tight, and works out. Are there any questions?
So we run into the same situation with dock walls all the time, and my question is, to fully pin the panel to the slab, and we have a pour back strip. How do you detail, and how are you detailing beyond that pour back to make sure that we're truly pinning the wall there and not missing out, or just engaging that pour strip and then there's not much else there?
Yeah, so usually what I specify would be, let's see if it shows up on the detail. Kind of hard to read, but essentially you call out for 2 to 4 minimum connections per panel, and then a 30 to 50 foot detailed area rebar. So you got the pour back where the dock leveler goes, and then that gets tied, usually actually welded, to a piece of bar that goes back in the slab. Under typical conditions, 20 to 30 feet of slab is enough to drag that load out of.
So you're counting on the friction of the slab then at that
Counting
point?
on friction of the slab, because I don't have a vapor barrier.
Okay.
So I get a pretty good cohesion to the slab.
And then another question I had was, at the corner panels where you come there, do you have any details showing your typical?
It's pretty simple. It's just a couple of embeds and an angle that gets welded together. It's not a structural detail. Like, you're not trying to transfer force across the joint. You're just trying to keep the panels, because as they try to move out, it really destroys the caulk joint, as opposed to side-by-side panels going to behave kind of together.
Do you see that if they're pinned together at that location, since we've got shrinkage issues on like the outer third of each panel, do you ever develop cracking around that?
I haven't seen too much cracking from that.
Okay.
I see many more of, and again, this is probably an excessive amount of weld, even though it's nominal. Really, you really just kind of want an inch or two of welding. But most of your cracking is going to come from the welding process and on the panel joint connections, right? It's not an expansion problem, it's a shrinkage problem with the thermal, right? The metal doesn't, it's as hot as it's going to be, and then it shrinks back when you weld the far side. So if you can keep your welding area to a minimum, it helps really cut down on the thermal. But yeah, I don't see too many cracks there.